In this video, we're going to do something a little bit different. We're going to have one signal, but it's in a more complex environment. There's two turnouts involved here and three different detected blocks. And the turnouts will be controlled via push buttons. And for purpose of this demo, rather than using actual block detectors, we will also use push buttons to simulate the blocks being occupied. In addition to that, this signal is going to be set up as an approach signal, which basically means that it will remain dark until the block it is protecting, or the block at which it's at the end becomes occupied. So when block 1 becomes occupied, the signal will go from dark to whatever aspect is intended to be displayed. You may want to refer to this diagram. You might want to take a screenshot of it or print it out or something so that you can look back as we're describing the configuration and see the items that we're referring to. Okay, we will begin as before by selecting a configuration. In this case, again, I'm just going to use configuration 1. We won't load it. We're going to basically start from scratch. First thing we'll do is define our signal, and in this case, again, it's going to be signal number 1. It's going to be a 3-light signal similar to the previous demo, and it's going to be on card 1 in position 1, and we'll save that device. The next thing we'll do is define the two turnouts that we have on this layout. So I will go to our list of objects here. I'm going to select a turnout control, and I'm going to enter number 1. And in this case, this is going to be a turnout that's controlled by a single output. I'm going to have this demo operating with a plug-in card that operates slow motion turnouts from a single output. So I'll select single control here. And the output I'm going to put on card 1 again, but I'm going to put it in position 9 on the card, which is in the second bank of outputs, the first position. I'm also going to create the second turnout, number 2, and that will be again single control on card 1 and in position 10, which is the second output in the second group. And I'll save that. Now I want to create the push buttons that we're going to use here. I'm actually going to use a different type of push button for this. For input number 1, to simulate block 1, I'm going to use a push button that is a push on off button. And the reason for this is so we don't have to try to hold down 3 or 4 buttons here simultaneously. We can operate these and we can set them on and set them off by pushing the button once or pushing it again. Block number 1 in the simulation is going to be connected to input 1 here. So I'm going to put this as input position 1 on our card and save that. I'm going to create 2 more push buttons. Number 2, again in a similar manner. Input number 2 and push button number 3, position 3. And those 3 buttons will simulate our 3 block detectors that we have. Now we also want to operate our turnouts, and I'm going to use these same type of push buttons to operate the turnouts. I'm going to number them push button 7 for turnout number 1. And the idea here is that when I push this button, it'll cause the turnout to change position. So I'm going to put this on card number 1 again, but in position 7, just so it'll be easier to keep track of. And I'm going to add push button number 8. And I'm going to put that in position 8 on our card. That gives us all the devices that we need for this layout. So the next step is to move on to doing the logic. The next step we want to take is to define the logic for controlling the two turnouts on the layout. So in order to do that, I'm going to select turnout controllers as my device. I'm going to select turnout number 1, and I'm going to say the default for this turnout is normal. So lacking any other input, the turnout will be in its normal or straight through position. Now in order to operate the turnout, I'm going to go to my push button, and as you recall, I'm going to use input number 7 to operate this turnout. So I'm going to say when input number 7 is on, this turnout goes from being normal to being in the reversed position. So I'm going to add in that logic line. That's all the logic we need for the turnout. And what will happen is the push button, when it comes on, and recall it was a push on off, so when it does come on, it will latch on. It will operate the turnout and move it to the reverse position. When it's pushed again and unlatched, the turnout will return to its normal position. So I'm going to save that logic, and then I'm going to do the same thing for turnout number 2. I'm going to say its default is to be in the normal position also, and I'm going to base it on input number 8 being on, and that will cause it to go to the reverse position. So I'm going to add that logic line, save the logic for that device. Now that basically gives us all the operation for the turnouts. Let's save our configuration at this point. And then the last step that we have to do is create the logic for the signal. Now this is going to be a little bit more convoluted because first of all, this is going to be an approach signal, meaning it's dark until activated. So I'm going to select signal. I only have one here, so I select signal number 1. And I'm going to say its default is dark. Now, we have to define the 3 states that this turnout can take. So let's start with and this is typically the case, we start with the most restrictive position, which will be red. So we're going to look at what do we need to do to set this turnout red, and there may be a number of different conditions. First of all, in order for the turnout to be lit up at all, block number 1 has to be occupied. So we're going to click input number 1 and say that must be on in order for this turnout to be lit. But in addition to being on, it will be red when, for example, turnout number 1 is in the reverse position. And if you look at the diagram, you'll see why that is. If the turnout's in a reverse position, we need to have a red signal to indicate to stop because the turnout's thrown the wrong way. Now, we'll say add this logic line. Notice that we have 2 terms now in this logic. We have the term for block 1 being occupied and also a term for turnout 1 being reversed. Similarly, we will say input number 1 is on and turnout number 2 is reversed. That will also give us a red condition because that turnout is basically part of the same junction, and both turnouts really need to be in the normal position in order to have the ability to pass through here. The third condition will be if when block number 1, again, and this term will appear in every one of them because we're doing approach lighting here. Block number 1 is occupied, but, excuse me, I made an error here. I'm using inputs, not blocks. but block number 2 is occupied, the signal will also be red, because we can't proceed into block 2 if it's occupied. So I'm going to add that. Now, I'm demonstrating something here that I didn't intend to demonstrate. So I just demonstrated something here I didn't intend to demonstrate, and that is I tried to create a logic here based on block number 1. You see this message up here. It says block number 1 has not been defined. I'm really using inputs, so I really need to change this to input number 1 being on as opposed to block 1 being occupied. If we had this set up as actual block detectors, then that would have been correct. Okay, so with that one being on and input number 2 being on also, we add that and we have a third term here, which is this signal is red when block 2 is occupied. That will be all the conditions that set the signal red. Now, let's see if we want to set this signal to a yellow state. What do we need to have for that? Well, in this case, we need, first of all, input 1 on, because otherwise the signal will be dark. We need turnout 1 normal. We need turnout 2 normal. But if block 3, which is input 3, is occupied, so input 3 is on, in that particular condition, the signal will go to yellow. So I'm going to add that logic line. Similarly, meaning input number 1 is on, block 2 is not occupied, block 3 is not occupied, and turnout 1 is normal, and turnout 2 is normal, we can finally set this signal to green. So we have actually 5 different lines of logic that can affect the state of this signal, and some fairly complex conditions here. So that will be everything we need to operate this signal in the manner that we want to operate it. So I'm going to save the logic for that signal, and I'm going to save my configuration, and then we can go on to actually download and operate this system and see what happens. Okay, I've now changed to the camera view so we can see the system in operation. Before I did that, I made one last minute change to the configuration. I realized that when we press the push buttons to select one of the 3 blocks that we're simulating, we had no way of knowing what position that push button was in just from looking at things. So what I did is I added 3 indicator lights, and you'll see them. They're the lights number 6, 7, and 8 on the little readout, and they will light up when the block is marked as occupied, or in this case when the push button is latched on. And that was just a simple matter of just creating indicator lights, and the logic just simply says when the push button is on, the light is on. I want to point out something else I've added here. We've got an interface board plugged into the second header here. This interface board is used to drive up to 8 slow motion switch machines, and I have 2 tortoises hooked up here to this board. In case you were wondering about the headers that are on the board, the reason, as you can see, maybe we have a 14-pin header here. The reason is each of these headers carries both 12 volt power, regulated 5 volt power, and ground circuit, so that boards like this one can be plugged in and can be operated directly from the power of the board that they're plugged into. Also, signals and other things like input sensors and so on can also be operated in the same manner. And the input and the output interfaces both carry the same power and ground, although of course obviously the inputs are connected as an input circuit, and the outputs are a power driven circuit. So if you recall the logic that we had set up, right now, because we have approach signals and none of the blocks are occupied, none of the signal is right here. The first three lights, red, green, yellow, is signal number 1. It's dark because the block number 1, which is the block that it's protecting, is not occupied. So if I press button number 1, you note, first of all, this indicator comes on showing the block 1 is occupied, and the signal goes from dark to green. Now, if any of the conditions occur that will set the signal red, you'll see, for example, if I turn one of the turnouts, I'll turn turnout number 1 to the reverse position here. The signal immediately, and the turnout moves, and the signal immediately goes to red. Similarly, if block number 2 is occupied here, the signal is also red. And same for the other turnout. If either turnout is reversed, the signal goes to red. The one condition that sets the signal yellow is when block 2 is vacant but block 3 is occupied. And you notice when I said block 3 occupied, the signal then goes to its yellow mode, and if I mark that as vacant, it goes back to green. Basically, that's the function of this particular junction setup that we have. And again, it was all done by point and click and downloaded to the card.